So what we're going to do here is we're going to look at a problem where we are treating a weak acid as a equilibrium problem. So in this particular case, we have phenylacetic acid as one of the substances that accumulates in the blood of people with phenylketonuria. It is an inherited disorder that in the severe cases can cause mental retardation and even death. A 0.085 molar solution of this compound has a pH of 2.68. Calculate the Ka value for this acid. So basically, like any problem, when I start out, I always write let C6H5CH2 COO minus, which is just this component of it, just ignoring the H, be the anion. And that allows me to summarize a lot of what I'm about to do. So I can then write HA, which is just this compound with an H on it, dissociates into H plus A minus. We're going to use our ice box. Set it up. We have 0.085 molar of the acid. I have 0 and 0 to start with. Now, I do have the pH of the substance is 2.68. And what that means is that I should be able to figure out the concentration of H plus, because we know that 10 to the negative pH is equal to the concentration of H plus. So in this particular case, 10 to the negative 2.68 is equal to 2.09 times 10 to the negative 3 moles per liter. And that is the concentration of H plus. So that when you have a pH, it is telling you the equilibrium value. So that's the equilibrium value of this. But because this is 1 to 1, that is also the value of this. So that means that I must have gained that amount for both the hydrogen ion and the anion. But again, 1 to 1 to 1 means that I must have lost that much for this. So now we just add up our lines. 0.085, take away this amount. This is significant at this particular point, and we end up with 0.0829 as the equilibrium value. Finally, we write our equilibrium expression. Ka is equal to the concentration of H plus times the concentration of A minus over the concentration of HA is equal to 2.09 times 10 to the negative 3. Since that's the same for both of them, we're just going to square it over 0.0829, and that's equal to 5.3 times 10 to the negative 5. That's how we solve a weak acid problem, specifically when we're looking for the Ka value. So now we're looking at a problem that deals with a polyprotic acid. And what a polyprotic acid is very simply an acid that can donate more than one hydrogen proton. In this particular case, we're going to use a very common acid that we would see in everyday life, which is citric acid, which is very common, obviously, in your citric compounds, which is things like lemons, oranges. So in this particular case, just like I've done before, I'm going to set up an ion, but this time I'm going to match the charge to negative 3, and I'm going to let this equal my citrate ion, C6H5O7 minus 3. Just defining that allows me to work a little bit easier throughout the problem. So in this situation, we have three acidic protons that are actually going to potentially come off. Very easy to identify this when you get an organic compound. Look for the one that has the H out in front, and that's going to basically show us that those are our acidic protons. So they work their way through the problem, and you can see that the number of H's is decreasing from the left to the right in each equation. And then obviously this is the first proton coming off, this is the second, this is the third. So we describe Ka1, Ka2, Ka3. And this can be found in the appendices of your textbook that show you exactly how what the Ka values are for polyprotic acids, and also will show you which acids are actually polyprotic. Just make sure that when you're doing this that you understand that these hydrogens are not acidic. They are bound either to a carbon, something that a bond that is not polar, therefore is not going to give up an acidic proton, where these H's are attached to the carboxylic acid group, of which citric acid has 3. So we have the 3 reactions written out, and we go up and we start looking at this value. So I have 7.4 times 10 to the negative 4. That's a fairly small Ka to start with, but we're going to continue to go through. So we're going to start by just dealing with the first reaction. So I'm going to write H3A, H2A, negative 1, so that's these two, and then H plus. Remember, I've defined what A is, and I'm going to use my icebox. And the icebox doesn't have to be used, it's just a great way to stay organized. So we are starting with 0.050 molar of the citric acid, and we're going to assume that we have none of this to start. Well, as soon as you see that you have a 0 on the right-hand side, that means that this side is going to be gaining just due to Le Chatelier's principle. So minus x, producing these ions. So 0.050 minus x, x, and x. So we're going to evaluate whether or not x can be ignored. As you do more and more of these, you'll begin to be able to kind of eyeball it whether or not you have to ignore x. But until then, you can just take the starting material, 0.05, and divide it by the Ka that you're dealing with, in this case Ka1. And you can see that the ratio is the ratio is only 67.56, which normally we're looking for a number around 500. 800 is probably a definite cutoff, but 500 is usually a good idea that we're going to be able to ignore x. So in this particular problem, we cannot ignore x. So what we're going to have to do is we're going to write out the equilibrium expression. H2A minus 1, H plus over H3A. And we're going to basically be ignoring steps 2 and 3 for a little bit. So now we just substitute in our values. So Ka1 is 7.4 times 10 to the negative 4 equals x squared over 0.050 minus x. So we're going to have a quadratic equation here. Basically working 7.4 times 10 to the negative 4, 0.050 minus x equals x squared. We multiply in and take it all to the same side, and we get 0 equals x squared plus 0.00074x. That's 0.00037, or 3.7 times 10 to the negative 5, which probably would be a better way to write that. Once you have the quadratic formula, you are going to solve it. Nothing really different here. Remember that your quadratic formula is like that. Normally I find that you're using the plus term, but you can go through and check it out, or you can use a calculator. Normally we don't need to see that work. And in this case, we find that x has two roots, -0.0064 and plus 0.005724. So x has two roots. They are both real, but one of them is negative, so it's immediately thrown out. So our value of x, so x is equal to the concentration of H plus, and I'm going to put a little subscript 1 to indicate that we're talking about step 1 here, which is also equal to the concentration of H2 is equal to 5.72 times 10 to the negative 3 molar. So we've solved our first step. Now we can start to have a look at a couple things. To start off, we're going to have just a look at what the pH would be. So remember what the pH is. The pH is the negative log of the concentration of H plus. So 5.72 exponent 3 minus. So I'm going to take the log of that. So the pH of this compound would be 2.24 if we did not take into account any of the future steps. As you remove a positive proton from an ion, in this case the citrate ion, as you try and take more positive protons away from something that's already negative, you'll notice that that reaction will be less and less favored. So we can continue on and do step 1 and look at step 2 and what that would actually look like. So for part 2, what we're going to be looking at is we're going to be basically repeating what we did in the first step, but for the second reaction. So we end up with H2A minus 1 going to H1A minus 2 plus H plus, my ice box. So now I know that I'm going to have an initial H2 or H plus step 2, and I know I'm going to have some initial H2A. So 5.72 times 10 to the negative 3 and 5.72 times 10 to the negative 3, and I have 0. So let me just get rid of this top part here. Within step 2, what we're looking at is how much hydrogen ion is going to be reproduced from the second proton to come off, which remember is going to be very unlikely because we have an ion that's already negative, and although there is a proton on there on a carboxylic acid group that is on a polar bond that is acidic, it still is quite unlikely that that will happen. So one of the first assumptions that we're going to make about this problem is that during the second step, the amount of X to come off is not that much. Even though when I take the 5.72 exponent 3 negative and divide it by the Ka for step 2, I only get 336. That ratio is a little bit concerning, but in a problem with a polyprotic acid for the second step, normally you can get a little bit freer with that approximation. If you do include the loss of X from H2A minus, then you're going to just get an answer that you'll see will pretty much get washed out anyway, but it might affect it in the 100th or 1000th spot. So we have the ice box, we're setting it up. We know that the change line is it should be fairly straightforward and easy, because anytime you have a 0, you know that that side of the reaction is going to be gaining. If you have multiple zeros, you know that the reaction is going to move in a way to try and reestablish equilibrium. So that means that there should be something in the reaction where the two zeros are going to be filled. It will do something. So this means minus X. So we end up with 5.72 times 10 to the negative 3 minus x, x, and 5.72 times 10 to the negative 3 plus x. So we write out Ka2 is h plus is h1a minus 2 h2a minus. So we write it out. Now, because I'm going to ignore that x, I know I had 336 as that ratio that we have been using, but I'm going to ignore it. It makes this problem a lot easier. So I end up with 1.7 times 10 to the negative 5 is equal to the concentration of H plus, the concentration of H1A minus 2 over the concentration of H2A minus. So what you're going to see when you go to do this is that the amount of H2A is 5.72 times 10 to the negative 3, and the amount of H plus is 5.72 times 10 to the negative 3. Those two values will cancel. So the concentration of H1A minus 2 is equal to 1.7 times 10 to the negative 5 moles per liter, which would also technically be the amount of H that has been produced in this particular step. But we know from step 1 that the amount of H produced is 7.2 times 10 to the negative 3. In step 2, we could expect somewhere in the neighborhood of 1.7 times 10 to the negative 5 for H plus as well. And when you add those two together, it's going to affect this spot of the concentration of H plus. So you would see somewhat of a difference, but it really isn't going to be that big of an issue. So with step 2 done, we're not really worried about the amount of H plus anymore. We're pretty confident we know where the pH is going to be. So we just need to go ahead and figure out what the citrate ion is going to be. So for the third proton, we have HA minus 2 going to H plus plus A minus 3. And this is the citrate ion. We defined that way up at the start of the question where we said let A minus 3 equal C6H5O7 minus 3. So we're going to look at the icebox. We have our starting material. And we have our amount of H plus, which really is just from step 1. If you go along the quadratic route for step 2, you might see a slight difference here. But again, the question says explain any approximation or assumptions we made. So I kind of feel like we can use those assumptions. We have a 0, so we know which side's going to be gaining. So 1.7 times 10 to the negative 5, 5.72 times 10 to the negative 3, plus x and x. So Ka3 is equal to the concentration of H plus, the concentration of A minus 3, the concentration of HA minus 2. So if it was unlikely that the second proton is coming off, it is very unlikely that that third proton is going to make its way off. But that could be controlled by putting this citric acid into a buffered solution at a lower pH. And we can talk about that a little bit more later, but in this particular case, in just putting citric acid into water, the third deprotonization is going to be very, very unlikely. So we ignored X in step 2, so that means we're going to ignore the gain of X in step 3 as well. So we take Ka3, 4.0 times 10 to the negative 7, and that is equal to 5.72 times 10 to the negative 3 times the concentration of A minus 3, all over 0.7 1.7 times 10 to the negative 5. So 4.0 times 10 to the negative 7. Let's just do this division. 5.72 exponent 3 negative divided by 1.7 exponent 5 negative is equal to 336.5. So A minus 3. So 4.0 exponent 7 negative divided by 336.5. So 1.19 times 10 to the negative 9 is the concentration of A3, and that's in moles per liter. So as we continue to have a look at this problem, I think we've solved everything we need to. We need the pH and the citrate ion. So C6H5O7 minus 3, which is citrate, its concentration is equal to 1.19 times 10 to the negative 9 moles per liter. And the pH of this is equal to the negative log of the concentration of H plus, which with my assumptions is all coming from step 1. So pH is equal to the negative log of 5.72 times 10 to the negative 3, 5.72 exponent 3 negative log negative. The pH is 2.24. And that's how we solve polyprotic acids.